Welcome to this presentation on the value of information in the earth sciences. Much of the material for this presentation is drawn from the book by the same name, Value of Information in the Earth Sciences, Integrating Spatial Modeling and Decision Analysis. My co-authors are Professor Joe Eidsvik from NTNU and Bhattacharjya from IBM. The book presents a framework for assessing the value of potential data gathering schemes by integrating spatial modeling and decision analysis. Various examples are used to show the concepts. Examples from energy resources, geophysics and geology, mining, forestry, conservation biology, and groundwater management. In these earth science decision problems, we use information, data, to build models, and then these models are used to help and guide decisions. So what is a decision? In decision science, a decision is something where we have an irrevocable allocation of finite resources. The decision maker has multiple alternate actions to choose from. There's some underlying uncertainty, and therefore the future prospects are not known. And the decision maker has some utility or value, different values for the different possible future outcomes. All of these make the decision problem challenging. If there were infinite resources, it would be easy. Similarly, if there was no uncertainty, that would be easy. And if the decision maker had no preferences, then the path would be easy. So decision science is a well-studied field. Science of decision analysis describes how people make decisions, how good decisions should be made, and also guidelines for decision makers. A decision in reservoir engineering might be where to drill production injection wells. So here we might have some alternative drilling locations and patterns. And the underlying uncertainty in this case is, of course, the geologic uncertainty in the subsurface facies distributions, spatial distribution of porosity, permeability, and pore fluid saturations. Another example of a decision problem in earth science would be, for example, mine planning and safety. At what locations within the tunnel should we stabilize the rock mass to avoid rock fall? And the uncertainty in this case are the uncertainties in the joint distribution and the joint intensity. So earth science decisions, you have to allocate finite resources, and there might be severe consequences, either big profit or loss, or the consequences could be in terms of safety and hazards. So before allocating these finite resources, the decision maker might choose to ask another question, make a second decision, and that is, should they gather more information about the uncertainty? Perhaps the new information could resolve some of the underlying uncertainties. And if so, then how much information should be acquired, what type of information, and of course at what price. So in the two examples, perhaps for the reservoir engineering example, seismic data might tell us something about the underlying uncertainty in the geologic facies distributions, pore fluid saturations. Maybe it's indirect and imperfect, but that could resolve some of the uncertainties. In the mine planning case, would additional borehole data tell us something more about the distribution of fracture intensity and the fracture counts? Would that help in making the decision? But is more information always better? It might lead to less uncertainty. Perhaps it might lead to a better Earth model, better in some sense. But is that better model going to lead to better decisions? If the information does not impact the decision, is it worth acquiring? So the decision theoretic concept of value of information says that information is not valuable unless it impacts decisions. So it links the information to the uncertainty as well as the decision. So there's an interplay between decisions, uncertainties, and information. When is information valuable? Three conditions have to be met. The information must be relevant, material, and economic, the pyramid of conditions. So relevant means that the observing that information can impact our belief about the underlying uncertainty. So extreme trivial example, while making a decision about whether you should take your umbrella to work, information about what your friend ate for breakfast hardly seems relevant on whether it will rain or not. The second condition in the middle of the pyramid specifies that the information must be material, in the sense that observing that information should have the capability to change the decision. And finally, of course, at the top of the pyramid is that the information must be economic. The price of the information must be less than its value. So that's the decision theoretic value of information. And the way it is computed, VOI is the value of the decision with the information minus the value without the information. The value of the problem, the decision problem, without the information. And value is a measure associated with each future prospect, each outcome, combined with alternative action. For example, this could be the profit. More general, it includes the decision maker's utility function and incorporates risk preferences, risk adverse or risk seeking. For this talk, we'll assume a risk neutral decision maker, and so we'll look at expected values. But it doesn't have to be that case always. So first we have to define the value without information, and that is always in the context of the primary decision problem. So there is a decision problem and there are alternatives, and each of those alternatives have some value to the decision maker. That's a value without information. And then the next decision is, should we gather information? And based on that choice, the information might tell us something, information A, information B. And then based on that, we again have that same decision problem. So here we see we have the initial decision problem, and then whether we gather information or not. And based on that, we again have that same decision problem over here, depending on the different possible information that we could expect to see. So it's always in the context of a primary decision problem. So VI analysis, in this sense, does not exist without defining that initial decision problem. So that's the value without information, the initial decision problem, the primary decision problem. So the workflow for VOI analysis first has to frame that decision problem. That's very important. And only then we can start studying information gathering, building spatial models, and so on. But framing the decision problem, the decision situation, is very important. There are other measures of information that are not directly related to any decision alternative. For example, information entropy, Shannon's information entropy, expected prediction variance, and they have their uses, of course. They can be used in certain contexts, but they cannot say whether the information is material or economic. They only address the relevance of the information to the uncertainty. It is not directly related to decision, these measures, so they are incomplete. VOI, the decision theoretic VOI analysis, is more complete, but it is more challenging to compute. It requires much more sophisticated modeling. So for the decision theoretic VOI, next we have to compute the value with information. And so we had the value without information, the primary decision problem. Then we have to compute value with information, and the difference is then the VOI. However, this value with information has to be evaluated before acquiring any data. So it has to incorporate possible future outcomes of that test. And then the value of this free test is compared to the price of the test. So some notation for decisions, uncertainty, and information. The uncertain outcome will be denoted by X. It can have multiple possible values. The set of alternatives are A. Cost for each alternative will be C. And the value function, for example profit, will be V, which is a function of X and A. It depends on the uncertainty as well as the different alternatives. Finally, the new information will be denoted by Y. So very simple example, pirate digs for treasure. Uncertainty is X, treasure or no treasure, alternatives dig or not to dig. Success, small chance of success, and you get a big payoff, and failure probability over here 1 minus B. So A, 0, 1, dig or do not dig. So here first we have to compute the prior value without information, and in this case you can build a simple decision tree. Small chance of the treasure, otherwise no treasure. We solve this, we average those with those probabilities, and then at the decision node we take the one that has the maximum value. So this is the expected value. Again, we are assuming that the pirate is a risk neutral decision maker. Not very likely, most pirates are probably risk seeking, but here suppose that pirate is risk neutral. We take the expected value, and then the prior value is the maximum of 0 and that expected value. In this case the prior value is just 0. So should avoid it because negative expected profit, risk neutral pirate. Now should the pirate consult a clairvoyant, perfect information. In this case the pirate will know beforehand 1% chance that there is a treasure and 99% no treasure, and based on that we'll take the action. So again we can solve the decision tree. At the decision node we take the maximum, and at the uncertain node we take the expected value, and we take the expected value of the max of 0 and the value. So in this case the posterior value comes out to be 1000, the posterior value with perfect information. And so the value of information, value of this perfect information, will be the posterior value minus prior value, risk neutral. And so if the price is less than this value, then yes, the pirate should consult the clairvoyant. But perfect information, not likely. So even though this is hypothetical, perfect information, it can still be useful. It is sometimes easier to evaluate the value of perfect information than the value of imperfect information, and this provides an upper bound. So this can be a quick initial calculation. Now when we have imperfect information, we have to now link this imperfect information y to our uncertainty x? How are they related together? And what does observing some y tell us about the underlying uncertainty x? Now, should the pirate get a detector, which is imperfect, so here we have, suppose the detector tells, it says k, what's the probability that it really is k, given that it is really k, what the detector says. So it's a fairly reliable detector, 0.95. And then we build the tree again. So the detector says positive, but of course it's imperfect. And you can choose alternatives, dig or don't dig. You can still maybe find treasure or not find the treasure. And we can again compute these trees and find the posterior value of imperfect information, 460. That's the calculation over here. And what we have to do now is we have to condition the value on the data y, but of course we have to account for all possible outcomes of y. So we integrate over all possible outcomes. That's this outer integral. And so in this case, the pirate will purchase this detector if the price is less than 460. So that's the value of imperfect information in this case. And this has to be conditioned to the imperfect information. So we have to understand the relation between y and the value. And then we have to integrate over all possible outcomes y. So of course, decision analysis and this concept of value of information is commonly used in many other fields. So what is special in earth science VOI analysis? What are some of the special challenges? So now what if there are several prospects, not just one prospect, and there is spatial relation between these prospects? So here's a BaseNet model of dependencies between different petroleum prospects in a basin, and they're related because ultimately underlying some of them they might have a common source and kitchen. And so then where should we develop, where should we acquire new data? And data at one location might tell us something about other locations because of this dependencies. So value of information for earth sciences, it's beyond univariate. We have to incorporate the spatial characteristics and geomodeling. It's inherently related to the geology. The uncertainties are spatial, so the spatial dependence now here. The alternatives are also spatial, where to drill, where not to drill, what patterns to drill. Value function is often spatial. It comes from flow simulation, that depends on the uncertainty and the alternatives. And the data are spatial. For example, geophysical data, seismic data, electromagnetic data, they're all spatial. So we have a spatial decision situation, and there can be different types of scenarios. Some where we have easily enumerated alternatives, a few alternatives, and the value is decoupled in the sense that the value just depends on that particular location. So we can really sum up over the spatial units. And on the other side, we might have fairly complex situations where there's high decision flexibility, a lot of alternatives, and the value is coupled, so there's no simplification possible. There's a whole range of spatial decision situations, low flexibility, decoupled value, and going on to high flexibility with everything coupled together. These problems, of course, will require different types of approximations and different levels of sophistication in our modeling. The spatial information gathering also could be perfect or imperfect information, and it could also be total or partial. Because information is spatial, we might choose to observe information at all locations or perhaps at a few of the locations. And we might want to observe perfect information at a few locations and maybe imperfect information at a large number of locations. So spatial uncertainty requires geologic modeling of the spatial relations, the facies, porosity, permeability, joint and fracture intensity, mining grades. Value function, it depends on the spatial uncertainty and the alternatives, so that will require computations, and the spatial information gathering. So when you're modeling geologic uncertainty, depending on the decision problem, we can have different levels of granularity or different resolution, if you want to call it that. At a global scale, a core scale, we might be interested in basin prospects. We might use base nets or geological scenarios. At a finer scale, we might have reservoir geomodels where we use multiple point geostatistics or other kind of models, surface and process mimicking models, to model the geologic uncertainty. Modeling the value function requires computation of flow or other process, maybe process of mining or process of groundwater remediation, and these can be computationally costly. Modeling the information requires understanding the relation between the geophysical data and the rock and fluid properties of interest, and this will also require modeling of rock physics, typically wave propagation or other kinds of physics. And so this creates a challenge in computing this VOI as formulated. As we saw earlier, we have this inner expectation condition of the data, and that has to be integrated over all possible data outcomes. And each of those can be quite challenging. So here's a approach, simulation regression approach, kind of a Monte Carlo approach, which can be useful in this situation. The basic idea is as follows. We simulate the uncertainties, so B realizations of those geologic uncertainties, simulate values for all alternatives and all of the realizations of the uncertainty, and we simulate the data using the forward physics. And then instead of inverting the data from the y to the x, we regress to find this conditional mean. Because we have this multiple training data, we can actually regress to find the conditional mean and use that. So I'll show you some of the examples of using this Monte Carlo based approach, Monte Carlo plus machine learning kind of approach, to help us with this challenge of VOI problems in earth science and environmental science decision problems. In our diagram, here we have our uncertainty x. It has some distribution p of x, and this informs our information, so p of y given x as well as the value, and these are the alternatives. Well, what we do then is we create samples of x, and then instead of inverting for x for each y and then getting to v here, we learn, using this Monte Carlo simulations, we learn the relation between value and the information. A simulation regression approach. So in the next set of slides, I'll show 3 different examples. One at a basin scale, prospect evaluation using Monte Carlo simulations. A reservoir scale where we look at the value of EM data using simulation regression, and then a reservoir scale looking at the value of time-lapse seismic. This is an example from the North Sea. We have 27 prospects, part of the North Viking Graben. There are uncertain geological variables, and these result in uncertain hydrocarbon volumes, and of course uncertain profits. The alternatives are prospect development decision, so yes or no at each of those 27 locations. The possible information could be exploration wells, which will tell us whether the prospect is profitable or not. Just a quick digression on what is Basin and Petroleum System Modeling, BPSM. So BPSM models 4 essential elements and 2 processes: source rock, reservoir rock, seal, and overburden, as well as trap formation and generation, migration, and accumulation of hydrocarbons, petroleum. This involves solving coupled nonlinear partial differential equations, and this is typically done using numerical solution, in this case finite element solutions. And the key modeling factors are the burial history, deformation, compaction of the sediments, thermal history, heat flow, source rock geochemistry, how the kerogen is converted to oil, and then fluid migration. Outputs are, of course, the history, how the reservoir compacted, the thermal history, geochemical history, and the accumulations. So that's the accumulation, hydrocarbon accumulation, which will be used in our calculations of the value. So we have 27 prospects, and we have the alternatives at each of those 27 locations. The uncertain geologic variables here are fault seal parameters, source rock parameters, geothermal gradients, and fluid migration parameters. So in this case, we perform the Monte Carlo runs. We have 500 realizations of the geological scenarios. These are input into the numerical modeling. And then the outputs are the hydrocarbon volumes at the 27 different prospects. And so first, let's look at the value before we have the information, the prior value. So these are the output volumes or the profits at the 27 prospects from the different Monte Carlo runs. And here we have the prospect number 1 to 27, and then the value, mean, as well as the percentiles. So here we see, in this case, prospect 26 seems to be the one that has the best prior value before we acquire any new information. And then from that on, we would perhaps go down to prospect number 25, 24, and anything below this line, of course, is not profitable. So as usual, VOI analysis, we have prior value, and then we have value with information. So in this case, to compute value with information, using those Monte Carlo simulations, we did a non-parametric estimate of that conditional expectation using k nearest neighbor estimate. And let's see what we get as a result. We have prospect number on the x-axis. These are the profits, the prior value, and this is the VOI, the difference between the value with information and the prior value. What we see here now is that, of course, prospect number 26 is still most valuable and has the most VOI. But now, instead of going down next to 25 and 24, we see here prospect 23 has become much more interesting because it has a large VOI. And that's because this prospect informs us about other prospects because it's spatially connected. Next, we look at an example, a reservoir scale example of the value of electromagnetic geophysical data. So in this case, the primary uncertainty is saturation, and this propagates to uncertain revenue and profits through porosity and thickness. Here we have one example of a spatial uncertainty that is modeled as a Gaussian random field, allows easy calculation in this case, and alternatives are to drill or not. And then we have to ask whether EM data, electromagnetic data, can resolve or reduce some of the uncertainty about saturations. because EM waves are sensitive to whether the rocks are filled with hydrocarbons or with water. They have very different electromagnetic response, resistivity response. So which of these survey lines, if any, west, center or east, will EM resistivity data help us to make better decisions? Not to reduce uncertainty, but to make better decisions. In this case, we use a Gaussian spatial model and we'll linearize the rock physics relations between saturations and the resistivity. And we do this because in this case then we can compare with the full simulation regression approach, where in one case we have the analytical solution and then the other one is a Monte Carlo solution. So we look at the comparisons here. VOI with 500 simulations for the 3 different lines, and here this is with 5,000. The simulation regression approach seems to give fairly good result compared to the analytical. Of course, here it's only possible because we assumed unrealistically a Gaussian model, and we also linearized the relation, the nonlinear relation between information and uncertainty. But nevertheless, this shows that the simulation regression approach is promising, as it can capture, in this case where the analytical solution is known. The next one, value of time-lapse seismic data, again using the simulation regression approach. Here we have reservoir uncertainty, so distribution of these channels is uncertain. We have production for 1 year, and then the decision is to these alternative, drill 1 or 2 of future wells, and so there are 15 possible alternatives. And of course we need to maximize the NPV. This example is done by our PhD student Geetarth Datta. So here are the decision alternatives. Gray shows the wells that are already drilled, and the black dots are the possible new wells, possible alternatives. So we have 15 of these possible alternatives. So before we address the decision, we then ask, should we collect 4D seismic data? And will the 4D seismic data tell us something about the underlying reservoir uncertainty? In this case, the spatial uncertainty is modeled by multiple point statistics, MPS, so it's non-Gaussian. We have the facies realizations, porosity and permeability, 1500 of those realizations. We have flow simulation to compute the forward changes in saturation for each alternative. And then we have rock physics and seismic modeling to compute the changes in seismic impedance. And then the value. The value, of course, depends on the uncertainty as well as the alternative, the 15 possible alternatives. And for each realization, we use a fairly standard net present value model that is typically used in these kind of models, in these kind of problems. This depends on the price of oil, cost of water produced, cost of water injected, and some discount rate. We also include the cost of drilling the wells. And then we have the rates, the water production rate, the oil production rate, and this comes from the flow simulations. Here is one example. For one of those alternatives, these are the sets of simulated oil production and the sets of simulated water production as a function of time. So first, of course, we need to compute value without information, the prior value. So in this case, we compute it over the set of realizations. And in this case, the best alternative is number 14. That gives the best prior value. But it is not the best alternative for all realizations, and that's why perhaps some information that will help to say something about the uncertainty might improve this decision. So the optimal alternative, given perfect information, is different for different realization. Hence, this indicates that VOI would be greater than 0. Here we have a score plot, an MDS plot, where each dot here represents one of the underlying geologic model, and we can see that the different realizations have different optimal alternative. For this one, for example, alternative number 12 is optimal. On the other hand, this one, this realization over here, alternative number 10 is the optimal one. Of course, we won't have perfect information. We'll only have imperfect information, the time-lapse seismic information, which will imperfectly say something about the underlying geologic uncertainty. And this will be different for different realization. As you can see, some realizations have these seismic time-lapse signature, which is kind of very elongated. Others have more localized, and some of the others have more distributed seismic signature. And the seismic signature are different for different realization, telling us that it has some information that we can use to perhaps make a better decision amongst the different alternatives. So again, the simulation regression approach, we have 1500 underlying geologic uncertainties. We simulate the time-lapse seismic data, and in principle we would have to invert each of those data to get P of X given Y and then compute the value. That would be very costly. Instead of that, we're going to use the training samples, the 1500 Monte Carlo simulations, to learn the relation between the data, the time-lapse seismic data, and the value directly. So we regress the values, which is the NPV in this case, on the changes in seismic impedance. If you do separate regression for each alternative. Before we do the regression, of course, we have to do dimension reduction, because here the change in seismic impedance is not just a single scalar value or even a curve. It's a map, it's a image. So there are various ways of doing this dimension reduction. We have tried out some of them. We can extract principal components, spatial principal components, kind of like eigenimages, and regress on those. Or we can extract a few features from the data, and then in this case we use random forest regression. So let's just take a look at that example. So here we have the seismic time-lapse information, the change in the seismic impedance as the reservoir is produced, and we extract some features of those areas. For example, the area, perimeter, centroid, orientation, so on. These are of course just 3 examples from 1500. And here are some examples of the regression. So this one is a random forest regression on those extracted features. We have the fitted value and the simulated value, and in this case we have fairly good correlation coefficients. And then we can use that in our VOI calculation. So in this case, with perfect information, that's a value, and then from this regression, simulation regression, we get these kind of values. So we just have a few hundreds of simulations, no inversion. because each inversion, if you were to do it correctly using, for example, Markov-Chain Monte Carlo, each inversion would require tens of thousands of simulations. Here we just use 1500 simulations and directly learn the relation between value and information. So those were quickly describing some of those examples. There are many more examples in the book, other applications, environmental applications, forestry, mining, and so on. So VOI in earth sciences, it's an information measure linked to decision analysis. And here we have VOI and decisions in a spatial context. And because we have the spatial context, there are actually opportunities for getting creative with the spatial information gathering schemes, and allows us a lot of flexibility of multiple spatial alternatives. VOI analysis in earth sciences requires integration between quantitative geologic modeling, decision analysis, and data science. Not only uncertainty quantification, but also how uncertainty and information can affect decisions. Of course, you have to note that for good VOI analysis, the conditional probabilities are case specific. They are related to that particular geology, whether it's a oil reservoir, it's a mine, or a geothermal resource. And it's based on experts in that field, geoscientific experts, as well as this model simulations, the simulation-regression approach that we showed. So of course, there's still many questions that are unaddressed, where we still have to do work and research. Where do we get required input probabilities? Have we considered all creative alternatives? That's very important. And then when should we do VOI analysis? Should we always do VOI analysis? Well, that's a question that comes up in all kinds of decision analysis. When should we do decision analysis? Should we always do this full rigorous decision analysis? No, it's not necessary to always do a decision analysis before every decision. It's only when we have serious consequences, profits, loss, environmental damage, safety, that we should do a rigorous decision analysis exercise. In other cases, it might be quite simple, quite intuitive. Maybe few quick rules of thumbs might be sufficient to come to a quick decision. So similarly for VOI, that also is a decision analysis problem, and in some cases we need not do a full rigorous VOI. There might be simple rules of thumbs, maybe the economics is quite simple, and so on. So it depends on case to case. So of course, when we do any VOI analysis, we should always look at the 3 points: whether the information is relevant, whether it's material, and then whether it's economic. And sometimes simple rules of thumbs or simple prior knowledge can help us to address those questions right away. Maybe it is not relevant, so no need to do any further VOI analysis. So VOI for earth sciences, what sets it apart from VOI in other fields? It is this integrating spatial geomodeling. That's really a challenge here that's very different. So spatial decisions, spatial uncertainties, and spatial information. To learn more, you can have a look at our book. The book has many other earth science application examples and comes with downloadable datasets and codes. Hope you enjoyed the presentation. Thank you.